Welcome to online course for learning computational fluid dynamics. My name is Dr. Pramod Kothmire. I belongs to School of Mechanical Engineering, MIT Academy of Engineering, Alandi, Pune. I am working here as associate professor and I am the course instructor for CFD, which is an elective course for mechanical engineering student, civil engineering student and chemical engineering student. So in this particular video lectures, we will be seeing the fundamentals of CFD. So the outline of my class is a course objective, the domains where CFD is useful, continuum mechanics role for computational technology, various approaches for engineers to solve the problems related to fluids, methodology, scope of CFD at various places in industry, CFD as a career, and finally conclude with applications. So course objective, these are the four course objectives we have designed for final year students, so that after learning this course for around 5 months, he will able to learn these four things. With this objective, he will be studying this course, and at the end of the semester, he should able to get the outcomes which are related to course objective. So first objective is to illustrate fluid flow and heat transfer problem using governing equation. Okay, which simply means that the algorithm, advanced algorithm will catch up with the flow physics and the governing equations and will try to convert it into computer programming. This computer programming will work simultaneously so that we will get the answer of the industry oriented problem, research oriented problems using simulation technique. Second important objective is to solve these governing equations. Okay, if you want to be a good CFD engineers, you should have a thorough knowledge of governing equations. And by using discretization as the method, you will be solving these governing equations. So there are three ways. One is finite difference method, finite volume method, and finite element method. All these three methods you have studied in the previous course, FEA, finite element analysis. So here we will be focusing on discretization method, which is related to heat transfer, that is conduction, convection and radiation. Third objective is to choose or to apply appropriate computational schemes for solving fluid flow and heat transfer problems. Many times for CFD engineers, it becomes challenge to solve the error or to debug the error, so that the computation of the simulations will go ahead and we will get the good results, appropriate results. Okay, for which many times it happens that we choose wrong scheme. So it becomes difficult for CFD engineers to get the proper solution. So this course will give you an idea for a particular group of problem which computational scheme will be best. Fourth one is we have already done with the laminar flow. This particular course we will be focusing more on turbulence modeling, okay, in engineering fluid problems. So these four aspects we will go ahead. Okay, now talking about the history, CFD is very advanced technique nowadays in the industry as well as in research centers. Okay, but this technology came into existence in the older times around 1940. Okay, where there was no computers to solve ODEs and PDEs. Okay, and the people used to solve this ordinary differential equation and partial differential equation of higher perturbation on a piece of a paper. Okay, so it becomes very much difficult. The process is very lengthy, it takes a lot of time and it is not reliable also. Okay, so Daimler Chrysler was the first company who have used or who have started with such type of technique, computational technique in automobile sectors. So later on, as the years go, there were different commercial software came into existence such as Fluent, Flowtron, Tidal, Gas, Splash, and nowadays COMSOL, OpenFOAM, etc. So these commercial softwares people are using to solve their problems, as well as many CFD engineers, they write their own code to solve the problem. We will move ahead. So these are the domains under heat and power. Basically in mechanical engineering we have four important domains. One is design, another one is heat and power, which is also called as thermal engineering. Third one is manufacturing, and fourth one is computer aided engineering. So under computer aided engineering we will be focusing on computational schemes, and we will be applying these computational schemes in this particular semester mainly on heat and power domain, because in FEA, finite element analysis, you have already used such techniques for solving structural problems. So this particular course we will be focusing more on heat and power domain. So there are various courses you have already learned in the previous semesters, such as thermodynamic in second year, fluid mechanics in second year, heat transfer and turbo machinery in third year, and RAC now simultaneously you are studying. So all these domains, apart from this, there are many other domains like cryogenic engineering, then gas power cycles. There are many domains of heat and power where we can use CFD very well. Okay, now first understand what is fluid mechanics. Okay, so in fluid mechanics mainly you have three sections. One is fluid statics, kinematic, and fluid dynamic. This all comes under fluid mechanics. So fluid mechanics is nothing but it is a branch of physical science which concerned with especially fluid and not the solid. So in fluid we covered liquid as well as gases and plasma or powdery materials and the forces on them. Okay, so the fluid mechanics is useful not only for a mechanical engineer, but it is very well and very important course for civil engineer, chemical engineer, biomedical, geophysics, astrophysics, and even nowadays biological students. Okay, coming to next. So what is a fluid? Okay, fluid is nothing but it has a tendency to move. Okay, even a minute amount of force is applied. Okay, here you can see three examples I have shown. One is spherical drop, second one is liquid in hand sanitizer, drop coilants. Apart from that, every places you will find there are particles which are easily to move without any major force. Okay, even with a small amount of force the particle move, we call it as a fluid, and the flow associated with it we call it as a fluid flow. We will classify it further. Okay, the classification is ideal fluid and real fluid. Ideal fluid is not existence, but we assume that viscosity is zero for ideal fluid. There are real fluids starting from water, mercury, so many are there, oils, kerosenes, gases. Okay, and one which is obeying Newton law of viscosity, tau is equal to mu du by dy, they are Newtonian fluid, and one which is not obeying tau equal to mu du by dy is non-Newtonian fluids. Coming to next, this is very important. Why continuum mechanics we should focus in computational technology? Continuum mechanics is what where solid mechanics is also coming into picture and fluid mechanics is also coming into picture. But the importance of the word continuum. A simple example I will give. You have a water in the glass. Now the glass contain water. Water will take a shape of a glass. Okay, if a glass is cylindrical in shape, it will take cylindrical. If the glass is rectangular in shape, it will take the shape of a rectangle. But when you will see at micro level, you will find the molecules of water, H2O. Okay, there is a bond between oxygen and hydrogen. Okay, and these molecules are dispersed continuously. We are assuming it is continuously they are dispersed. Okay, there is no space between two water molecule. That is, there is no void space. Okay, so when we are assuming that there is no void space, it is continuous. Okay, so in solid mechanics as well as fluid mechanics, there is one domain where we will assume that molecules are continuously distributed in a given phase. So we call that as a continuum mechanics. Okay, so here you can see it is between solid and fluid mechanics. Now in fluid mechanics I already told we have fluid statics and we have fluid dynamics. Of course fluid kinematics get covered in fluid dynamics where it is bothered only about velocity and acceleration. Okay, and then we will be focusing in this particular course on this particular thing, mainly this particular thing. This is what CFD come into it. Boundary problems, boundary conditions. Okay, then multi-phase flow. Okay, we will be studying different set methods. so that we can able to simulate multi-phase flow problem, because for reactor designs, for pharmaceutical industries, for heat exchangers where more than one phase come into picture, we need to have multi-phase flow. Okay, boilers, okay, reactors, heat exchangers, aerofoil, jet propulsions, everywhere multi-phase flow is important. So we will be focusing on multi-phase flow also along with turbulent flow. Then stability. What is the problem stability? That is very important. Okay, whether the simulations which we run are giving you appropriate results or not. One should able to check that also. Okay, and then the problem which are related to internal as well as external flow. Okay, so that this is what about the continuum mechanics, solid versus flow. Now, even though the name of the course is computational fluid dynamics, we can use CFD for solving problems related to structural analysis. Mainly it is used for fluid oriented problem. The reason behind this is, you can see in this slide, you can see solid particles, they are organized in a proper fashion. You have studied BCC structure, you have studied FCC structure, whereas fluid particles, they are randomly organized. They take the shape of the container in which they are filled with. Okay, so here you can see the example. It is what structured, properly packed structure. Here it is randomly arranged, and when it is going into this particular cylindrical vessel, it will take the shape of this vessel. This is a gas. It is having a lot of freedom. Intermolecular force of attraction is very less, so all the molecules are randomly arranged and they are filled in the cylinder. So these are the three examples I have shown, okay, where you can see a major difference between solid and fluid. In solid, you require a proper amount of force so that the deformation will take place. It is rigid, whereas fluid, even a small minute amount of force will allow this particle to get dispersed, to get deformed. Okay, so that is why the computational technology is very useful for doing the analysis or doing the experimentation or doing or interpreting the results with fluid rather than solid. Because solid, we can do experiments, the observations are okay, observations are valid, okay, we can rely on those observations. There are very quite few chances, okay, where you will get uncertainty in solid related experimentation, whereas fluid, there is a lot of uncertainty. Error bar is very important when we conduct experiments with fluid, because fluids, they change with the movement of time also. Okay, in morning you will get some different results. Same experiment if you will do in noon, in the evening, early morning, it will give you different reasons. So as soon as the ambient will change, the observations related to fluid will change. So computational technology will make us easier life to overcome with these challenges. Okay, so moving ahead. So already I discussed difficulties or the challenges with fluid flow is, it is difficult with experimentation, difficulty in observing or recording localized data, difficulty in construing data, and the overall cost is also very high. Okay, type of flow. Okay, I told you that in last semester we have focused on laminar flow. Of course, I will be showing you few simulations of laminar flow using COMSOL multiphysics. Okay, where you will able to see different nature of the fluid particle as far as velocity is concerned, as far as shear stress is concerned. Okay, and then this particular semester we will be focusing more on turbulent flow, the schemes, the modeling which is associated with turbulence flow. Okay, so in general there are these 6 type of flow you have studied in your second year fluid mechanics: steady, unsteady, dependent on time, and dependent on type, uniform and non-uniform, dependent on space, independent of space, laminar and turbulent flow depending upon the particle movement. If it is layer by layer, laminar; if it is zigzag, chaotic, it is turbulent. Compressible, incompressible, rotational, irrotational, 1D, 2D, and 3D. Okay, turbulence. Okay, so turbulence is mainly associated with the fluid particle at higher velocity, where it normally undergo irregular fluctuations, mixings. Okay, and it is opposite to laminar flow, where the fluid particles are moving layer by layer in the smooth path. Now different modeling we will be studying associated with. Few examples we have shown here. You can see turbulent flow of a boat wake. There is a very high velocity. You can see lot of eddies are formed around the boat. Okay, this is nothing but the turbulence, disorder, okay, in the movement of water particles in the direction of boat. Okay, now there are various approaches by which engineer can solve the problem of heat and power. Okay, the four approaches are very famous. One is analytical, which is purely related to theoretical. Then second one for which we are learning this course, that is numerical simulation, which is a CFD. Third one is experimental. By drawing the graph, we get certain results. And fourth one is the analogical, where we compare two different physical equations which are bounded by similar boundary conditions. Okay, where we can use the formula established in one system to the similar systems and we can get the solution. So out of these four, the most advanced ones is numerical simulation. Experimental, it take lot of cost. Nowadays you can see so many aerofoil industries, aircraft industries, they are successful with their first design without making any prototype. Why? Because they spend a lot of time with numerical simulation. Computational simulation make it so easy that after spending a quality time we get a successful design, and without making any prototype, even though if we make the actual model, okay, the model gets successful, work very efficiently. So this is the beauty of CFD. Okay, it the expenses which we spend on doing experimentation and prototyping is saved, okay, because of CFD technology. So what exactly is CFD? CFD is the tool used for interpreting or forecasting the fluid flow results in complications of simultaneous flow of heat, mass transfer, phase change, chemical reaction, basically the transport phenomena, where there is a transfer of mass, transfer of energy and transfer of momentum, okay, using computers. So these are the comparison. I already explained why the CFD is important as compared to experimentation. Experimentation will give you the thorough results. They are most truthful, faithful, okay, and they are actual. But CFD will save lot of time, and within a less amount of money, you will get more and a reliable result. So this is the basic ideology.